This is video 24 in our series Topics in Tensor Analysis. The playlist for all the videos is at the website digital-university.org. In the last two videos, we had spent some time considering that if you have a vector and you take the derivatives of the components of the vector, that those collections of partial derivatives that we have do not comprise a tensor. They don't transform like a tensor transforms. And in this video, we want to consider that same question, and I'm going to try to approach it from a more intuitive viewpoint. Now remember from our first 2 or 3 videos that if you have a vector and you have, say, a curvilinear coordinate system with coordinate axes x1, x2, x3, and so forth, and then you have a y curvilinear coordinate system with axes y1, y2, y3, and so forth, that the way the components of the vector transform, here we are in the x curvilinear coordinate system, and here are the covariant components of the vector. Then in the y curvilinear coordinate system, the covariant components are found by using this equation. And for the contravariant components, they transform according to this equation. And again, we had covered these in the first couple of videos. Now, we'd also considered, suppose that we label our curvilinear coordinates like this, where we have u1, u2, u3, u4, and so forth. And then the other one is labeled as u'1, u'2, u'3, u'4, and so forth. They're going to transform the same way, of course. Here are the covariant components of the vector in the u coordinate system, and here's how they would transform into the u' coordinate system. Now here, we were using the labels x and y so that we know which curvilinear system we were in, just like we did right here. But in most textbooks, they don't label it like that. They'll just simply say, put a prime above the v and leave this one with no prime mark, so that we know here we are in the u system, here we're in the u' system, so the equation is written like this instead for the covariant components. And then the contravariant components in the u system and in the u' system, again, transform the same way. So here, if, say, we're in the x curvilinear coordinate system, if this is a 0 vector, then obviously it's going to be 0 in the y curvilinear coordinate system. And of course, that's going to hold throughout all these different transformations. So if a vector is 0 in one coordinate system, then it's going to be 0 in all the other coordinate systems. And of course, that holds true for tensors too. Here we have just a second-rank covariant tensor in the x curvilinear coordinate system, and here it'd be its components, its covariant components in the y curvilinear coordinate system. They transform by these set of equations, and here would be for contravariant transform. Here the contravariant components transforming from the x curvilinear system to the y curvilinear coordinate system, or a mixed tensor transforms. So clearly, if we're in the x coordinate system, if this is 0, this tensor is 0, it's going to be 0 in the y curvilinear coordinate system. And of course, that's going to hold true throughout. So if a tensor is 0 in one coordinate system, obviously it's going to be 0 in all the coordinate systems because of the way the transformation equations are set up. But now, let's consider this kind of a situation. Here we have Cartesian coordinates, and we have a vector field that is constant everywhere. Remember, when we're in Cartesian coordinates, we just speak of the components of a vector or the components of a tensor. We don't make the distinction between covariant and contravariant components because in Cartesian coordinates, they're always the same. Now, let's look at this. Here, the vector field is always constant. So, if we're going along, say, the x8 axis, then the component along that axis is always the same. Same thing for the x1 axis. The component of the vector field along the x1 axis is always the same. Or for any horizontal axis, the components stay the same, and for the vertical axis, the components of the vector field don't change. Now, if we had a more, say, a complicated vector, say something like this, or here for the I component we have 13 times x to the 26th minus 19y to the 5th plus 8 times z to the 47th. We have more complicated terms for the j unit vector and the k unit vector. Of course, this is not going to be constant. This is going to change everywhere. And here, say just for the I component, we could take the derivative of it with, we're in three-dimensional space, we can take the derivative of this with respect to any one of the coordinate axes, the x-coordinate axis, or take the derivative of this with respect to the y-coordinate axis, or take the derivative of this with respect to the z-coordinate axis. Obviously, we're going to get non-zero expressions. But here, where it's constant, where the components are constant everywhere, if we take the partial derivatives, then it's going to be equal to 0. But let's consider the same vector field not in Cartesian coordinates, but in a curvilinear coordinate system. So suppose that we just have two curvilinear coordinate axes, y1 and y2. The vector is always constant. Now let's consider its contravariant components. Those are the components along each coordinate axis. So here, say if we're in the y2 coordinate system, the component of it along the y2 axis here is going to differ than what it is here. Same thing for the y1 coordinate axis. The component of the vector on the y1 axis here is going to be different than what it is here. So even though the vector is always constant, if we take these partial derivatives of its covariant or contravariant components with respect to the different curvilinear axes, now the derivative is not 0 because the components are always changing because the curvilinear axes are always changing in shape. So here we have where in the Cartesian coordinates the derivatives of the vector are always 0, but these collection of partial derivatives that we can make, they don't behave like a vector or a tensor, because if these are 0 in this coordinate system, then if they behave like a vector or a tensor, they'd be 0 also in this coordinate system. But that doesn't happen. Also, if we took partial derivatives of the covariant components, those two would come out to be non-zero. So here's an example then where derivatives of vectors are not behaving like vectors or tensors. In this case, they come out to be 0, but in the different coordinate system, they are not 0. Let's just take one more simple kind of an example. Let's say that we're just in two-dimensional space. Oh, something we can say here. This demonstrates the fact that you can have a vector that is constant from point to point in space, but that doesn't mean that its components are constant in space, because the curvilinear axes are always changing their orientation. So when you have a vector space, how its components behave depend on two things: the magnitude and orientation of the vector, and it also depends upon whether the axes are continually changing in orientation. Now here, let's just consider, here we're in two-dimensional space, and we have Cartesian axis and polar coordinate axis. Now here we can have a point P. Here would be then a radial unit vector. Here would be an angular vector. So if we had some vector here, we could express it in terms of radial components and angular components. Well, what happens if, say, the angular component is 0? So then our vector field will have only radial components. And let's say that the magnitude of those radial components is 1. So we have a vector field of unit length radial components. What would that look like? So like something like this. Here we have just radial components, no angular components to them, and they have equal length. They're unit radial vectors. So here, 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 here. In polar coordinates, this vector field is always constant then. But clearly in Cartesian coordinates, it's not constant. In Cartesian coordinates, this has no x2 component. This one has no x1 component. Here, this has an x1 component and an x2 component. So does this one, but clearly the x1 component and the x2 components are different. So in polar coordinates, if we take partial derivatives of this unit vector with respect to either the radial axis or the angular axis, that partial derivative is going to be 0. But if we take the partial derivatives in the Cartesian system, they're not going to be 0. So again, a demonstration that when you have a vector and you take partial derivatives of its components, they don't behave like vectors and tensors. If it was, then these partial derivatives are 0 in the polar coordinate system. If it was behaving like, if these partial derivatives were behaving like a vector or a tensor, then they would also be 0 in the Cartesian coordinate system. And again, that doesn't happen. So just kind of an intuitive demonstration that when you have vectors or tensors and you take derivatives of their components, you do not get a vector or a tensor. And let's just quickly review how we had demonstrated that explicitly in the past two videos, video number 22 and video number 23. In video number 22, we had Cartesian coordinate system and a curvilinear coordinate system. We had a vector in Cartesian coordinates and that same vector in curvilinear coordinates. And we were in d-dimensional space. We took the partial derivatives, got a d-squared number of terms. In the curvilinear coordinate system, we took partial derivatives. We obtained a d-squared number of terms. And then we asked ourselves, these collection of partial derivatives, the d-squared number of them, do these behave like a tensor? If they did, then these would transform into each other. We're taking covariant components here, so they would transform into each other the way that a covariant tensor transforms. And what we discovered was that did not happen. And then in the last video, in video number 23, we had considered just same situation, only from a curvilinear coordinate system to a different curvilinear coordinate system. We took the partial derivatives in each case in d-dimensional space. So in each case we had a d-squared number of terms, and then we asked ourselves, this collection of partial derivatives, did they behave like the components of a tensor? If they did, then these partial derivatives for these covariant components, they would transform into here the way a covariant tensor transforms. And that didn't happen. Specifically what we saw was here is how a second rank covariant tensor transforms from one curvilinear system into another curvilinear coordinate system. So here we have d-squared number of partial terms in the x curvilinear or in the x Cartesian system. Here we have d-squared number of partial derivatives in the y curvilinear coordinate system. If these are the components of a tensor, here and here, then they should transform according to these set of equations. This and this cancel, so this partial derivative should be equal to just this simple expression. But what we found in video number 22 was that, no, these partial derivatives transform according to this equation, where we had this term, but we picked up this extra term here. And the same thing happened when we just considered going from a curvilinear system to another curvilinear system, taking partial derivatives of covariant components, and asked, did these transform like a tensor? If they do, then if these are transforming, here's the d-squared number of partial derivatives in the unprimed system, here's the d-squared number of partial derivatives in the prime system. If they're transforming like a covariant tensor, because we have covariant components here, then they would transform according to this equation. Or here, this and this cancel. So the partial derivatives of these primes should equal this simple expression. What we found in the previous video was that the partial derivatives of these primes instead transform according to this equation. We have this term, but again, we picked up this extra term. And in each case, here and here, this extra term that we pick up is due to the fact that the curvilinear axes are always moving around, and therefore the components of a vector are always changing, even if the vector itself is constant in space. And that's what results in this extra term that we pick up in each case. So the bottom line is that when you have a tensor and you take, or a vector, and you take derivatives of its components, those derivatives do not behave like tensors. So the question is there a way that we can modify the differentiation process? So if you have a vector or a tensor, can you go through a modified differentiation process so that what you form is another tensor? And there's a way that you can do that. It's called covariant differentiation, and that's what we're going to do in the next video. So come back, join us for that video, and we'll take a look at how the covariant differentiation process works.